All right, what I want to do next is I want to show you how to solve a differential equation that's really unlike anything we've ever seen before. Y double prime plus e to the x times y is equal to 0. Okay, so this e to the x times y, just to be clear, I probably could write it the other way, y times e to the x. Maybe that's a little clear, but this is difficult. This is not like anything that we've done before. It's definitely, so this is actually a linear equation in y, but you drastically do not have constant coefficients. So all of our previous methods just fall flat on their face, and we're left with really only the power series method here. So what I want to do is I want to take y, and we're going to do the usual thing for y. So y is going to be some power series c sub n, x to the n goes from 0 to infinity. And we also want to recall e to the x. So e to the x, if we write it as a power series, I'm going to center e to the x at 0 because that's where we've centered our power series, is at 0. So this is going to be 1 over n factorial x to the n. Okay, so that's our power series for e to the x. And just to expand on these a bit more, let's actually write out what these are going to become. So this is really going to be equal to, we know y is just c0, c1x, c2x squared. We know that whatever the subscript is, that's going to be our power, right? That's exactly how this works. And I'm just going to write out a few more, c3x cubed, c4x to the fourth, and so on. Okay, and we know that e to the x, if n is 0, we're going to get 1. If n is 1, we get x. If n is 2, we get 1/2 x squared. If n is 3, we get 1 over 6 x cubed. If n is 4, we get 1 over 4 factorial x to the fourth, and so on. Okay, so again, just taking those up to x to the fourth for each term. And so what I want to do now is I want to actually come up with a power series for their product. And we're not going to do anything fancy. We're just going to write the power series for each of these. So this is c0 plus c1x plus c2x squared, c3x cubed, and so on, c4x to the fourth. And we're going to multiply that by 1 plus x plus 1/2 x squared, 1 over 6 x cubed, 1 over 24x to the fourth, and so on. And now I'm just going to distribute. The only constant term that we're going to have is c naught times 1. So that's going to be c naught. Okay, that's the only constant term we're going to have. We're going to have two linear terms. We're going to have c1x plus x times c naught. So c1x times 1 plus x times c naught. Okay, those are going to be the constant. Those are going to be the linear terms that we have. So c1x plus x times c naught. And then let's think about how we're going to get a quadratic term. Well, we could take an x squared over here with a constant over there. We could take the product of the two linear terms, or we could take this x squared multiplied by c naught. And so those three are going to give us, those three terms are going to give us a quadratic, all our quadratic terms. So we're going to have c2x squared plus c1x squared plus 1/2 c naught x squared. And then let's do just one more term up to x cubed. There's going to be 4 terms, but we're going to have c3x cubed and 1, c2x squared and x, c1x and the 1/2 x squared, and then finally c naught and 1 over 6 x cubed. And we're going to add all those up. So we're going to get c3x cubed plus c2x cubed plus 1/2 c1 x cubed plus 1 over 6 c naught x cubed. And then we just keep doing this for as many terms as we want. But this gives us a power series for y times e to the x. So that power series that we're going to get for y times e to the x is going to have a constant term, c naught, plus our linear term, right, c naught plus c1 times x, plus our quadratic term, so it's going to be 1/2 c naught plus c1 plus c2 x squared, plus our cubic term, which is going to be 1/6 c naught plus 1/2 c1 plus c2 plus c3 x cubed. All right, and so finally, there's our power series for y times e to the x. That's how you multiply power series. There's really nothing fancy going on there. There's, of course, formulas for multiplying power series, but that's the process. The formulas just basically hide the fact that we're just distributing. Okay, we're just distributing power series with infinitely many terms, but other than that, it's exactly like distributing polynomials. So there's y times e to the x. Remember that we were trying to solve, our differential equation that we were trying to solve was y double prime plus e to the x equals 0. So let's just move y times e to the x to the other side. Let's try and solve that. We have a power series for the right side. That's actually the hard part of this problem, is getting that power series. And y is going to be the same. So we already have a formula for y. We know that y is c sub n x to the n. And so that means that y double prime is going to be n times n minus 1, c sub n, x to the n minus 2, is n goes from 2 to infinity, right? This is a story that we've seen many times. So that's what y double prime is. And what I want to do now is I could set this up where on the left side I write, I substitute in our second derivative for y. On the right, I substitute in our power series. And in a way, that's what I want to do. But rather than actually write out the formal sum on the left, I'm just going to write out what terms we get. So let's think about what's y double prime. So if n is equal to 2, which is it's our starting value. If n is equal to 2, what we're going to get is we're going to get 2 times 1, c sub 2, x to the 0. So this is y double prime on the left. And if n is equal to 3, we're going to get 3 times 2, c sub 3, x to the 1, plus, and we're just going to keep going. If n is 2, we get 4 times 3, c4, x squared, and then one more, 5 times 4, c5, x cubed. Okay, and again, infinitely many more terms. That's going to be equal to the power series that we have, which is minus y e to the x. Remember that we found plus y e to the x. All we're going to do is literally just change the signs to minuses, right? All those are going to become minuses. We're going to have minus c naught minus the quantity c naught plus c1 times x, minus the quantity 1/2 c naught plus c1 plus c2 x squared, and then one more, minus, let's see, this is 1/6 c naught plus 1/2 c1, c2, c3, all times x cubed. And then we have, again, infinitely many more terms. And so we have a power series on the left, a power series on the right. They both start at the same place. And so they both start with constant terms, right? X to the 0 is just 1. And so what we get from this is actually we can just equate the power series term by term this way. So this is another way to do all these problems. This happens to be what I think is a much better way to think about this. So it's kind of a much better way to think about this, at least for this particular problem where you had to multiply the power series. And so what we're going to do is just equate the power series. So we know that 2c2 is going to be equal to minus c naught. And so that's what we get from here, setting that equal to that. And then next we know that the linear terms have to be the same. So 6c3 is going to be equal to minus quantity c naught plus c1. And 12c4 is going to be minus the quantity 1/2 c naught plus c1 plus c2. And one more, 20c5 is going to be equal to minus the quantity 1/6 c naught, 1/2 c1 plus c2 plus c3. And we can keep going. Now, again, there's two ways to think about this recurrence. It's a second degree recurrence, therefore we're going to have two terms that we get to pick for free. So C0 is 0, C1 is B. Equivalently, this is a second degree recursion, because what we're doing is each of the values is going to depend on the value in the sequence that's 2 terms back. Okay, so this is a second degree recurrence. So that's what's going to happen. So we got C0 is A, C1 is B. And again, if you just want to think about it as you have no restrictions on C0 and C1, that's fine. And so let's think about what's going to happen for C2, C3, C4, C5. And so this tells us that C2 is going to be negative 1/2 C0. So that's going to be negative 1/2 A. And C3 is going to be negative 1/6 times C0 plus C1. So that's going to be negative 1/6 times the quantity A plus B, or negative 1/6A, minus 1/6 times B. And then let's just do 1 or 2 more. I guess let's just do 2 more. I've already written it out to C5. So C4 is going to become negative 1/12 times the quantity 1/2 C0 plus C1 plus C2. So that's going to be negative 1/24 times C0 minus 1/12 C1 minus 1/12 C2. And that's going to be negative 1/24A minus 1/12 B minus 1/12 C2, which we said was negative 1/2 A. So that's going to actually give us, oddly enough, these are going to cancel. We're going to get negative 1/24A minus 1/12 B plus 1/24A. Okay, just by good old dumb luck there. And that turns out to be negative 1/12 times B. And then finally one more, C5. So going back up to our formula here, C5 is going to be negative 1/20 times the quantity 1/6 C0 plus 1/2 C1 plus C2 plus C3. Yeah, we don't need C4. Okay, we just need up to C3. So that means that we're looking at what? We're looking at negative 1/120 C0 minus 1/40 C1 minus 1/20 C2 minus 1/20 C3. And that is negative 1/120 times A minus 1/40 times B minus 1/20 times C2. C2 we said was negative 1/2 A. Minus 1/20 times C3. C3 we said was negative 1/6A minus 1/6B. And so that's going to be, we just have to figure out what's going to happen here. We're going to have negative 1/120 times A minus 1/40 times B plus 1/40 times A plus 1/120 times A plus 1/120 times B. And so that simplifies to, so negative 1/120A plus 1/120A, those cancel. And let's see. That means that we're left with 1/40 times A plus 1/120 minus 1/40 times B. And that works out to be, this works out to be, let's just do it. We got 1/120 minus 3/120. So 1/40 is the same as 3/120. So it's going to be minus 2/120 or minus 1/60 B. Okay, and that's C5. And we're still, remember, trying to solve for y. So y, as always, is C0 plus C1x plus C2x squared. C2x squared. C3x cubed plus C4x the fourth. C5x the fifth. And that's where we stopped. So that's a plus bx plus, now we just have to go back and remember what all of our values were. C2 is negative 1/2 a, so that'll be negative 1/2 a. That's the x squared constant. C3 is negative 1/6a minus 1/6b. So negative, let's think about how to write this here. Let's do it like this. We're going to have negative 1/6a minus 1/6b, x cubed. And I'll come back and we'll simplify that when we can. C4 happened to just be negative 1/12b. So let's say x4, x to the fourth constant. And then C5 we just found to be 1/40a minus 1/60b. That's the x to the fifth term. And so now we're going to do the usual thing where we factor out the a's and factor out the b's. The one thing that's going to be new is that now we're going to have a's and b's that might possibly have the same power, but everything is fine. So let's just get all the a's out. We have a minus 1/2 ax squared minus 1/6ax cubed. There's no a in the x to the fourth term, so we're going to have plus 1/40 ax to the fifth, and so on. And for the b terms, we're going to have bx minus 1/6 bx cubed minus 1/12 bx to the fourth minus 1/60 bx to the fifth, and so on. And so again, we have a time, you can write this as a times 1 minus 1/2 x squared minus 1/6 x cubed plus 1/40 x to the fifth, and so on, plus b times the quantity x minus 1/6 x cubed minus, get out of here, minus 1/12 x to the fourth minus 1/60 x to the fifth, and so on. And again, we have our two linearly independent solutions. I know that they're linearly independent because one's not a multiple of the other. They don't have the same powers of x. Even if they did have the same powers of x, their coefficients are not multiples of one another. Okay, so we know that they're linearly independent, and that means that we're done. We found our two linearly independent solutions. Okay, and so again, these are the solutions to the equation y double prime equals negative y e to the x, and that's about as complicated as this gets for these types of series problems.